Okay, so good morning and welcome to the last lecture.
Good morning, Professor.
So I sent to some of you, the one that gave me the email address, some samples for the exam. So I don't know if you had a look about them. If you have questions.
Yes, Professor.
Yeah, so let's start with the questions then.
I think in the sample 1, second question. In sample 1, the second question, and I think this sort of question appears in all the samples, and I don't know how to argue that this is a compact operator and find eigenvalues.
Okay.
I was confused by
So
it.
let me copy the text and then we study. Yes, and this is a classical example, so it's a very good question because this is a classical in a lot of exams, and even if you want to apply for PhD courses, very often they ask you compact operator, and they say, give me an example, or they give you this kind of stuff. So the exercise is exercise 2, sample 1. So now I give you an operator k from L2, and here is from minus pi to pi into itself. Defined by kf evaluated in x is equal to the integral from minus pi to pi of t minus s fs ds. Okay, so this is a general, okay, so the question is that K compact self-adjoint, and of course you have to find eigenvalues. Eigenvector. Okay. Okay, so first of all, let's see that it is an operator. Well, from L2 to L2, and then it is trivial because, K is an operator. So K belongs to the linear operator from L2 into itself, simply because, so let's say this is step 0. Okay, because what we apply here, holder in, well, you can apply whatever you want. You can say that this is in L infinity and this is in L1 simply because for the measure of the set is finite, or you can apply holder directly. So for example, holder, so let's say that the L2 norm of this guy so the minus pi to pi, okay, let's compute it. So let's give you for any g, just do in this following form. Minus pi to pi, the integral gt, sorry, this was t, xt. And then it's the integral t minus s fs ds dt. Okay, and then, okay, this is the integral ft fs gt t minus s. Okay, and this is less or equal than, okay, we can estimate with the L1 norm, for example, just for simplicity, f1, g1, and the supremum of this guy, phi minus pi to pi, which is 2 pi. And being in a bounded set, so we know that in a bounded set, the norm of f, okay, this is by holder, so let's play in 2 is less or equal than the norm of f 2 to the, sorry, the norm of f1 is less or equal to the norm of f2, and then here we have the measure of the set, which is in our case is 2 pi to 1/2. Okay, everything together, you get 2 pi squared. Okay. So it tells you that this object here is in L2. No? Because when tested with L2 function, you have something which is bounded. And its norm is 2 pi squared most the norm 2. Okay, you can have even better estimates. We don't care. No? So K is a linear operator. So let's see that K is compact. So we have to find essentially that if this is bounded by 1, okay, the image of the set lives in the compact set. Now observe the following. This guy here is Lipschitz. This is the property of many kernels. So in the book there is some note about, for example, Hilbert-Smith kernels, Hilbert-Smith operators, which is actually this guy here. So, but in any case, we do for the specific example. So the observation is that this guy is Lipschitz with norm 1. Okay? So T maps to T minus S is 1 Lipschitz. Or there are even better things. So I think, well, let's start with this idea. So I'm going to say then Kf is, I'm saying, is 1 Lipschitz. Okay, not 1 Lipschitz. Okay, is, okay, let's see which is the norm. If norm of F 2 less or equal than 1 is not 1 Lipschitz, you get some constant. So let's compute it. So Kf, this is one possibility. Yeah, there are several, many. T minus Kf T prime, by definition, is T minus S, T prime minus S, Fs ds. Okay? But now T minus S minus T prime minus S is less or equal than, okay, let's put a modulus. So the absolute value, we don't have to care. So it is the integral. So the difference is 0 whenever T is not between S, whenever S is not between T and T prime, no? So the difference of the object, you make a graph. So I give you T, I give you T prime, I have the difference of these objects. Okay, well, it's not 0, it's a constant. So minus pi, so from pi to minus pi, and so at most, well, the difference is this thing here, which is T minus T prime. So it is the L1 norm of this guy, which is square root of pi, of 2 pi, no, or F2. Okay, so if the norm of less than 1, the image is a function which is 2 pi Lipschitz. Okay? And now 2 pi Lipschitz function, so we conclude by showing, or just showing, well, just showing. This is just observing, because it's an observation. So the 2 pi Lipschitz, or square root of 2 pi, sorry, square root of 2 pi, is a compact set in C0. Because, okay, we have that it is we have to verify that it is bounded, but let's see that the norm of Kf of T, so the supremum, is less or equal than, okay, the maximal of this thing, which is 2 pi, the integral of f from minus pi to pi, so less or equal than 2 pi to the 3/2 norm of f2. So it's a compact set in C0 and C0 is embedded clearly as a stronger norm. So can be embedded continuously in C2. No? So it is a compact set in C0, and it's certainly a compact set with C2 norm, with the L2 norm.
Professor, what is C0? It's
so C0, C continuous, just my mistake. It's continuous. Okay? Then we can see another proof. So another proof is that, well, you know that since the space is reflexive, essentially it is it is Hilbert even more. Another proof is let Fn weakly convergent to F, norm of Fn less or equal than 1, then Kfn should strongly converge to Kf. And then it means that it's compact, no? This is equivalent, I mean in Hilbert, but even in reflexive, to compactness. Okay, let's prove this. So if it converges, then you observe that Kf of t, Fn of t is the integral of t minus s, Fn of s in ds, and now you observe that this guy converges because Ft minus s belongs certainly to L2. So if this converge weakly, and this is in L2, it converges to t minus s Fs ds, which is equal to Kf Ft. So it means that you have pointwise convergence. And now, well, we have the bound plus the uniform bound, which is the one that Kf of t is less or equal than, 2 pi to the 3/2. Okay, let me write this. And now you apply Lebesgue-dominated theorem. So the integral of Kf okay, this guy is bounded by a measurable an integrable function, and it converges pointwise. So this guy converges to what is the pointwise limit? Converge pointwise to 0, so it is 0. So we deduce that it's compact simply because the image of weakly convergent subsequences is a strongly convergent sequence. Weakly convergent sequence is a strongly convergent sequence. Okay? So let's do point B. So in any case, this is a full class.
Professor.
Yep.
Can you go through the proof again? I don't think I quite understand it.
Okay, so there are two different proofs of the same fact that is compact. So the first proof, I prove that I show that the image lives in a compact set, or pre-compact set, okay? The image of the unit ball is a pre-compact set. So the pre-compact set here is the 2 pi Lipschitz functions bounded uniformly by 2 pi to the 3/2. And why is a compact set? Because it is certainly compact set in the continuous function, and the continuous norm is a stronger norm than L2, so C can be continuously embedded in L2. So if it is compact here, it is certainly compact here. So the first proof shows that the image is contained in this compact set. So I have to compute the Lipschitz constant and the L infinity DC norm, the continuous norm, the infinity norm, the supremum norm, whatever you want to call it. So let's take the difference. So by definition, and then you just observe that maximal difference of this guy is the difference of the 2 points. And then you estimate by Holder. So this goes out, it doesn't depend on S, and this guy is always 2 pi, square root of 2 pi, the normal F2 by Holder. And the same Holder inequality is for the L infinity norm, because the maximum of this difference is 2 pi, so you bring out 2 pi and then you compute it. Or you can even better, you can just apply Holder directly to the function and you get a better estimate, it doesn't matter. This is the first proof. Is that clear?
Yes.
The second proof is that I use the fact that the compact operator, when I'm reflexive, certainly for Hilbert, are characterized by the property that if I have a weakly convergent sequence, its image is strongly convergent. Okay, so I want to verify this fact for my operator. So I take a weakly convergent sequence and I compute the image, and now this is the definition of the operator. Now, this guy belongs to L2. It's bounded, so belongs to L2 of minus pi pi. So the limit, since it converges weakly, this means that when tested with any linear functional, in particular the linear function defined by this function, it converges to the value of the linear functional in the limit. And the value is the integral of this guy, which by definition is again the operator evaluated in T. So the result is that his function converges pointwise to the limit function. Now I want to pass to the limit. So because what I have to prove that this guy goes to 0, and I know that the pointwise convergence of this guy. So whichever estimate allows me to pass to the limit, for example, the dominated convergence. So let's find a function which dominates this quantity here. Well, it was already computed, and it is given by this estimate here. So these functions are in L infinity, and the bound is uniform. Well, it's some constant. It is not the best, but doesn't matter. So these functions here are in particular bounded. So I can pass to the limit. So the limit of this integral is equal to the integral of the limit, which is 0. Conclusion, if I have a weakly convergent subsequence, its image is strongly convergent, hence K is compact. Okay?
Yes, Professor.
Yes, and the thing is that you, as I said, this is very important. It will certainly be asked sooner or later. So let's see the second part. So now I can cancel. So eigenvalues and eigenvectors. Self-adjoint. Sorry, I have to prove that it's self-adjoint. So self-adjoint. So what do I mean self-adjoint? Okay, this is a real operator. Well, it can be even complex, doesn't matter. Let's consider for the real, as in our case. So we need to prove that GKF in the scalar product of L2 is equal to KGF. So let's do that. This guy is the integral GT KFT equal to, by definition, so I'm doing this part here, GT integral T minus S Fs ds equal to Fubini theorem Fs integral GT T minus S and this is equal to Fs S minus T because the module is symmetric. And this guy, by the way, is the other guy. Okay, so it's self-adjoint. Okay? Now let's see eigenvalues and eigenvectors. Is that clear, the other part? Self-adjoint?
Yes, Professor.
So now it's self-adjoint, so basically we know that there are only eigenvalues and eigenvectors. They form a base. There is no other part in the spectrum. Well, okay, there is 0. 0 is always a critical point, but we don't need that D to compute the eigenvalues. Okay, so we need to solve. We need to solve KFT equal to lambda FT. So this is an eigenvalue, so it's the kernel of lambda identity minus T. So the kernel should be not empty, not 0. So let's write the thing. This is the integral from minus pi to pi, t minus s, fs ds equal to lambda ft. So now what I observe, I come back to the thing here, and I see that this integral is Lipschitz. So I deduce f of t is Lipschitz. Because otherwise, because it is the image of this guy which has been estimated to be a Lipschitz function. So now I think you have seen in real analysis that Lipschitz functions are differentiable almost everywhere. Okay? So now we compute the derivative.
Professor, it's differentiable, not almost everywhere, because f is continuous, and under the integral we have continuous function. Integral of continuous function is always differentiable, C1 function. We can show that f is differentiable.
Yeah, but wait a minute. You don't know yet that this guy, okay, if you want to, it is the second step. Once it's Lipschitz, you put it inside this guy, and then you can differentiate twice. But so far, this is just an L2 function, so I don't know why it should be integrable almost everywhere. Okay, so but in any case, it doesn't matter. Let's compute the derivative. We can, so the derivative, okay, I don't know if to do the exercise. The exercise is that this guy has derivative which is bounded by 1, so everything is bounded. I can pass to the limit, so I can use uniform boundedness. So I can use Lebesgue dominated convergence. And then I get that a lambda f prime of t is equal to the integral from minus pi to pi. And this is what? The sine. So its derivative is the sine of t minus s, fs ds. And then I discover now that this guy is, well, okay, this guy is, it holds everywhere by continuity. Then f prime is continuous. And, okay, it holds, okay, if I prove it, this is the formula. Well, I discovered even more. F prime is Lipschitz. Why? You take the difference, so let's do it. So lambda, if for lambda different than 0, of course. So lambda, sorry, f prime. So, okay, we have just to compute the difference of these two guys. Minus pi to pi, the sine of t minus s minus the sine of t prime minus s. And then it is fs. Okay, and well, was the same computation as before, just changes the thing. So this is 2 only when s is between t and t prime, so it's less or equal than, okay, in this case it becomes t prime, well, it's square root t prime. Okay, this doesn't matter, it's really t minus t prime for some constant, which is the L1 norm of f. And we have already an estimate of this guy, so less or equal than a constant t minus t prime. So I can differentiate twice. So, okay, so what is the second derivative of this guy? The second derivative is, okay, here I have to use that the derivative of this guy, I don't know if you know that the distributional derivative is the delta in t, is 2 the delta in t. Okay?
I didn't get that, Professor.
Pardon?
What do you mean by delta?
You don't know the distribution?
No.
Sorry, that's a problem because I wanted to use the distributions. Okay, so let's write what is this integral here. So it's lambda f prime of t is equal to the integral from minus the integral from minus pi to t of fs plus the integral from t to pi of fs ds. Okay? Okay? This is the definition. I just exploited the definition of the sine function. And now, what is the derivative of this guy? Now, you know the fundamental theorem of calculus, no? This guy is continuous. This guy is continuous, so the derivative of this guy is what? Is minus f of t. And the derivative of this guy is again minus f of t. So finally, I discovered the following thing. Lambda should satisfy okay? Okay, so now we have to solve, I think, let me think just 1 second, because then I can solve that as a linear function, and then I have that the kernel should be this guy. So for t, I'm looking if there are some boundary conditions here, so let me think. T, I don't see, I have to compute that. Okay, so we know that f should be a solution of this ODE, and then we can compute it. Because this is just a linear ODE, no? So it's, well, another thing that I observe is that k is positive. Because it's self-adjoint, and the kernel is positive. Wait, is that true? Yeah, it's true, but I wonder how to prove it easily. I'm looking to a fast way to get the eigenvalues because I need some boundary conditions here. Not so sure. I don't see how to get them. More complicated than what I thought because now I have well, it's like this. I need to solve this ODE. So this is f second minus 2 over lambda f, and now there are two cases. So if, but this is certainly a positive operator. So sorry, k is greater or equal than 0 simply because in the base kf f is equal to lambda f. Well, okay, let's keep like this. Because if I don't know that this is positive, I have two solutions. But so one is f. Let's do the other stuff. F is equal to, so let's see this guy is omega squared. So it's a cosine of omega t plus b sine of omega t. Like the kernel because the kernel is not the best, but okay. And so now I know the form, and omega is the square root of 2 over lambda. So now I plug it inside the formula, and I have to get an equation for lambda, which is the integral t minus s. Okay, cosine of omega t plus b sine of omega t dt. Okay, and this should be computed, and I get a very ugly expression. And so I wonder if the exercise, the second part is, well, this can be done, and because this is equal to lambda a cosine of omega t plus b sine of omega t. However, it seems a little bit the computation long, so I wonder if there is a short way. Which I don't, I'm sorry, now I don't see any short way, and the computation is clearly too long for a text. But okay, but this is the way. So you arrive to a relation, which is, in this case, an ODE. In general, it would be, well, it is whatever. In general, it is an ODE. You solve it, and then you plug inside. And so to get the ODE, you have lost some conditions because the integral condition is more than the ODE. So once you find the form of the solution, you have to check that it satisfies your original condition, which is this integral here, which unfortunately is a little bit more complicated than what I thought. So, okay, maybe I can send you the solution if I find something faster. Otherwise, I stop here because we see the way. So we find the eigenvectors, which is something of this form. And you normalize by A and B. You have to normalize that to 1. And the eigenvalues is because once you have this equality for any t, the lambda cannot be arbitrary, and you can compute it by, okay, you have to integrate this guy, and you get a relation between omega and lambda, which should match this relation here. So the lambda should be a particular choice. It's a little bit long. I don't see any short way now. I'm sorry. I can send you if I think I see something short. Otherwise, okay. I'm sorry. I think if there are other questions, otherwise we lose the whole time just to compute this integral here. Strange that I thought when I wrote it, I thought was slightly easier. I'm sorry. You see any short way to get the eigenvalues, which is not this way, but I don't see this. I think this is the only way. Yeah, because yeah, there is no way. Yeah. I'm sorry. Are there other questions on the exercises? Okay. By the way, did you? In any case, you see the line how you have to study the second question, no? Who, I don't know who was the guy who asked the question, but I hope.
Me.
Who? Sorry.
It was me.
Okay, which I don't see, but.
Ajay.
Ah, okay. Yes. Okay. Okay. I can send you if I find a simple solution. I can write. I can compute the computation and give you the solution. But it's it takes. I mean, it would take too much time. And it's already 30 minutes that we are doing on this exercise. It will be easy. I mean, the first part is okay. The second part will be easier. I will check that you have something which can be computed easily. So the approach is always you have, for these integral operators, these integral operators are translated into an ODE relation, an ODE relation, and you solve it. And usually, so the solution should be solution of the integral operator, which is more than, so it is, so it is more than just being the solution. So this relation here gives you more information, and in particular, it will give through this equality how are the relation between omega, lambda, and A and B. And then when you solve it, you get the eigenvalues. Okay, I thought it was easier, sorry. Usually is easier, right? When I just take a variation and was more difficult than what I thought. Okay, are there other questions on the samples?
Can we discuss 4B, Professor?
4B, or even
Yeah.
this. Okay, so let's see the whole exercise. So we have a subspace of L infinity, which is given only by let's say the points in L infinity such that xn is different than 0 only for finitely many points. Which is C compact. So this is equal to C compact, no? Small c compact. Okay. A and closed or compute.
Sorry, Professor. It's finally many what?
Many numbers. So finitely many numbers n. So finitely many n, let's say. Which is called also the space C compact. Every function is continuous because the n is made of isolated points. So, or it is closed or compute the closure. So that does not exist. a linear functional on the dual such that f on C compact is equal to 0. And C, the closure of M intersection the unit ball has no external point. Okay. So, what is the closure of M? Since you do not ask, you know. So, what is the closure?
M is closed set.
So, who asked the question? I think he knows what is the closure, no?
I was thinking it's C. It must be C naught.
C0, yeah.
Yeah.
Okay, and then it is an easy exercise because I don't know if you does anybody wants me to show it or you just see?
Please show it, sir.
Pardon? Show?
Please, we would like you to show it.
Okay. So first of all, M. So you have to prove two things. A. So let's say C0 is closed in L infinity. Because, okay, this is a classical thing. So an L infinity means that, so C0 is a sequence xn such that the limit tends to 0. Now if you have x, so xn, xk, which minus x in norm infinity, so this is the supremum, let's say. So let now xkn be a sequence in C0 such that, okay, this is converging, there are even, well, no, this is not, such that, okay, it converges in L infinity, so xk converges to x in L infinity, and so the norm infinity, this means the supremum over n of x k evaluated in n minus xn, it tends to 0. And actually being in C0, this is a maximum. So now what we can say? Now, so we have to prove that the limit of this guy is in C0. So this means in particular that for all n, skn converge to xn pointwise. And then we have to show that this guy is small. So now what we have that okay, if xkn, the supremum, let's say minus xn is less than epsilon, so there is very small, then the lim sup for n which tends to infinity of xn, I write like the lim sup xn minus skn plus xkn. And now, this is less or equal than epsilon, this is 0, so it is less than epsilon, so the lim sup is less or equal than epsilon. And this shows that the limit of this guy can be as small as I want. So it is 0. And this gives exactly that it is a closed set. So any limit belongs to the set. So C0 is closed. Now I have to prove that the finite sequences are dense. So if X belongs to C0, then there exists, then for all epsilon, there exists, let's say, capital N, Xn less than epsilon for all n greater than m, because it's in C0, so that, let's say, x prime n is equal to xn n less than m, 0, for when this guy is forward, satisfies x prime m belongs to C compact, so my space M, and, okay, this is not a good choice. N, sorry, this is N. And what is the distance? So is 0 up to n bar, and from n bar on is bounded by epsilon. So my space is dense, and the C0 is closed. Conclusion, m bar is C0. So now we want to see that this does not hold. Okay, let me think if I have some fast way. So I would take the double. This is one. Okay, this is very easy. So, the question was different. Is the kernel of F is equal to C0? So the question is much easier than what I thought, because is that one, no? Okay. If there exists F, so recall the following. The kernel of F has codimension 1. Okay? So the kernel of a continuous linear function is a closed subset with codimension 1, which means that I need just to add a vector in order to get the whole space. So if there exists F such that the kernel of F is equal to C0, then L infinity is equal to C0 plus any vector which is not in C0. So the real numbers times any vector not in C0. Okay, so let's show that this is impossible. But let's say two vectors. So let's say xn equal to 1 for all n, and xn equal to minus 1 to the n for all n. They cannot be, cannot be written, let's say x prime equal to, let's say, alpha x plus beta y, where y is in C0. Okay, this cannot be possible, because if this holds, when, okay, let's say, so let's see this fact a little bit better. This would mean that x prime, so minus 1 to the n, is equal to alpha plus beta yn. But with yn tends to 0 as n tends to infinity. And you see that is impossible, no? Because after a while, this guy is small, very small, less than 2. And so you cannot match minus 1. Okay? Is that clear? Is that clear now?
Yes, Professor.
It's much easier, because the other thing is that, on the other hand, and this is not in the side, but on the other hand, there exists f in the dual such that, and f is different than 0, such that f in C0 is equal to 0. Can you give me an example? I think we have seen the lecture. Was the limit functional, no? If you remember. The limit functional is a function which is in C0 but is non-zero. I mean, the extension of the limit function. So let's show that this guy doesn't have any extremal points.
Professor, by linear functional, do you mean we take limit of Cn? F of x is equals to limit of x?
F of x, yes, the extension by Hahn-Banach. So
Okay.
you extend by Hahn-Banach f of x is equal to the limit of n xn. This is given only on the subset of, and in this subset, what is interesting is that this subset is defined on the sequence which has limits. Sequence which has limits is a closed set, and let's say if you define L is xn such that there exists the limit of xn, then here it's true that the limit functional, so let's call this functional f bar, restricted to L, is equal to C0. So the fact is that L infinity is much larger. So the last about, let's do the extremal points. I think I can cancel here. So it is m bar, intersection, less than or equal than 1. Okay, so what about the theory here? This set is bounded, closed, strongly closed, convex, and so it is weakly star closed. Weakly star convex. So let's take any point. So assume that So what is yn? So let's say x bar n, x bar is an extremal point. Which means that if there exist y and y prime in this set K, such that 1 minus t, y plus t, y prime are equal to x, then y equal to y prime equal to x. Okay? So now what is the idea? The idea is that since x of n tends to 0 as n tends to infinity, then okay, xn is less than 1 for some n. Definitely at some point should be less than 1. So there exist, let's say, two vectors. So there exist, so let's say that less than 1 for n, for some n. So say this is equal to alpha, and this belongs to the open set. So we can compute it. So now take epsilon equal to the minimum 1 minus alpha, alpha minus 1, so which is modulus of 1 minus alpha. And the two okay, y is equal to x plus, okay, let's say yn, okay, or y is equal to x plus, let's say, epsilon half e of this n, and y prime is equal to x plus minus epsilon half this en. So, and en is the standard thing. So it's 0, 1 in the n position. And then 0 again. So clearly what happened is that 1/2 y plus 1/2 y prime is equal, since they are opposite, is equal to x. And, well, I just increase or change the value in one point, and since I choose epsilon exactly this guy, y prime are still in K. So there are no extremal points. Okay? So because I proved that if there exists an extremal for any point, I proved that it's a linear combination of other two. So let's go back now to the theory, just 1 second. So this is certainly weakly, so it is convex and then it is closed, so it's weakly compact. It's weakly closed. Okay? However, what is the weak star closure of K? Or let's say, or yeah, K is okay. If you want to verify, the weak star closure of K is equal to the unit ball. Because, okay, we know the implication, the embedding C0, the dual of C0 star, which is equal to L1, and the dual of L1 is equal to L infinity. And so the embedding is that and we know that the embedding of C0, so, or let's say the theorem that tells you that I think was the concept of Hadley's lemma. In any case, the C0, the weak star closure of C0 is L infinity. Because the weak star closure of the original Banach set, when embedded in the B dual, is the B dual. There are no other functions than the one in the dual. This is what it says. And so the thing is that this is clearly convex, strongly closed, weakly closed, but it's weak star closure, which is the one which would allow me to prove that it's compact, is, however, the unit ball. So the extremal points are in the unit ball. Indeed, the unit ball has extremal points. Okay, so this is the second. Are there other questions? Did you understand now? I mean, I enlarged the answers to see some theory, but just to verify why the thing works. Are there other questions?
Professor, what is the, I think there is a typo in the statement of the question 5 in the very last equation in inequality. What does E, is it just a product?
So the J be closed and considered closed subset?
No, I mean in the very last line.
But in this sample, exercise 5,
Yes.
closed subset E.
It's Ft is equals to Gt times the norm of F less than C.
No, wait, this says that for there exists a F. So, okay, so let's see the exercise. This is a uniform bound. Sorry, this should be open mapping. No? So the exercise is J is contained in 0, 1, closed, and let E is a subspace of the continuous function in 0, 1, with the property that for all G in continuous function of this closed set, there exists an F in E such that Ft is equal to Gt. Show that there exists C dependent of G such that for all G in C, J exists F E such that norm of f, okay, extending, okay, less or equal than c norm of g, and f of t is equal to gt. Where is the site? Where is the print? I don't say. Correct, no?
Oh, okay, I see. I think it's not a product. I think it's ft equals to gt such that this inequality holds.
Yeah. So it's clearly true when I take the whole space, no? Because I take the supremum, I can have extended. So the thing is just that you have a subspace. And this is closed. Of course, you need to have closed. Okay, so the thing is just by the standard stuff. Okay, so what we have now, we have that we can take the map of the operator. So for all G, there exists, so we have an operator which is the restriction, let's say R, which acts on E and maps to C of J, which is defined by R of F is equal to F restricted to J. And the assumptions here is that R is surjective. Surjective because, well, it's by definition, for any G there exists an F. Hence, so now we can use the open mapping. By open mapping, we know that the R of the ball, let's say, which are all the F, in norm CZ, in the continuous norm, is less than 1, contains all the G whose norm is less than C. So this is the continuous on 0, 1, and this is the continuous on J. On J, no? This is by open mapping. So this which means by scaling that, so you see, if I have a G whose norm, so now I scale by norm of G, that there exists, that for all G, there exists an F, so whose image is G, so R of G, R of F is equal to G, and the norm of F is less or equal than, okay, the scaling is 1 over C. Because it's enough to have, well, if I have to reach norm of G, it's enough to take 1 over C, and then you observe that the scaling is correct. Okay? So it seems correct, no, the exercise. Other questions?
Is it RF what?
RF is FJ, so RF.
The last line.
RF equal to G.
Okay.
So the image of the restriction of F is equal to G.
Professor?
Yeah.
In sample 2, question 5.
Is not this one? Ah, no, this was sample 1, sorry. Gosh, I forgot. So sample 2, question 5. Is this one that you wanted to solve, to say that there is a typo, no?
No, I don't know. The second B, is the answer to B just psi?
So you want to say, let me see. So psi, so I have to write everything. It's better because maybe the other they don't know. So let's see the exercise. So exercise 5, sample 2. So we have psi, which belongs in L2 of 0, 1, is given. And we define k psi is the u in L2, 0, 1, such that u is greater or equal than psi, almost everywhere. So now the first point is the minimization. So the problem, the minimum, 0, 1, u squared, okay, as a solution, as a unique solution. And B, that compute it. Okay, so what about point A? Point 8 has been covered by the theory because this is what? Well, this is, okay, there are several points. Let's see. One is the direct proof. So we have that, so this is the norm squared, is lower semi-convex and lower semi-continuous. So in particular, okay, lower semi-continuous in the weak norm. Because if I forget everything, I mean, I can forget the theory, but because this is well, let's see, this is really the direct proof. So, and so this guy here, K phi, is closed and convex. Okay? It's closed because if you have a sequence, if UN converges to U in L2, then up to subsequences, UN of X converges to U of X, and being this is greater or equal than psi t, we deduce that is greater or equal than psi x, sorry, psi x. And convex is trivial because the convexity leaves the inequality invariant. Okay, so we have to minimize the function, let's say the function f of u, which is the norm of u squared, plus the indicator function, sorry, plus, let's say, if u belongs to k, and plus infinity, if u does not belong to k, is convex, lower semi-continuous, and so we know there is a minimum, and coercive, let's say, coercive. Since we are in a Hilbert space, and so the convex lower semi-continuous functions are, and coercive functions are lower semi-continuous, and they have compact subsets for sufficiently low values, so there exists a minimum. Or I can do even something else, so I can think that this is, so it is the projection of 0 on K. So is the minimal point, so u psi, so my minimal point is the closest point to 0. And then I apply the theory of projection, so u psi exists and it is unique in Hilbert space or in convex space, in uniformly convex space, or strictly convex space, sorry. Okay?
Professor, how do I rigorously write this second statement? It is the projection of 0.
Oh, because what is the projection of a point? Projection of K of a point, of a value, let's say V, or let's say G, okay, is the U such that U minus G is the minimum over all F or V. So it's U in K such that is a minimum of V minus G. And now take G equal to 0, and you discover that you have to minimize exactly the norm squared. Okay?
Yes.
Okay, so now we know that it is the projection. And now let's compute it. So, well, if I know that this projection, it's much easier to get what is the U psi. So the projection is characterized by, so is okay, I'm projecting, let's say, so it's the U. So recall the following. If I forgot I have the drawing, so this is the projection. So let's say this is G. This is the projection of G. So this is U, which is the projection. If I take another V, and I take the scalar product of these two vectors, is less or equal than 0. So it's characterized by G minus U, U minus V, sorry, V minus U, less or equal than 0 for all V in K. Which reads, in our case, G is equal to 0, so it means that U, V minus, let's say, he says U psi, let's say, U psi, V minus, let's say that U is greater or equal than 0 for all V in K, and which reads that, so it's, so U is greater or equal than psi, and U, V minus U greater or equal than 0 for all V greater or equal than psi. Okay? Okay, so this means what? Well, it means that since V can go to plus infinity, comes to remember that U so it means that what? That U is less or equal than 0 almost everywhere, because what happens that v in particular can tend to plus infinity, no? So v minus u can be as large as I want. So I just observe the following, that if h is greater or equal than 0, then u plus h is in my compact K, and then u h is less or equal than 0 for all h greater or equal than 0. So I get that u should be less or equal than 0. On the other hand, u should be greater than psi. So the projection, so what happens? That but I mean, there is something that doesn't work. Why is so? Why I get stuck here? Something that doesn't work when it's negative. Maybe I changed it, I made some mistake. There is an inequality which doesn't work because it should be the reverse thing. So because I know the solution should be u is the max between u and 0. That is the solution, but and I have an inequality which is in the wrong direction, and I don't see why. Because it is really the projection, p minus. The thing is correct, should be the guy. Ah, no, it is, so it's not, it's greater or equal than 0. Gosh, it's stupid. This is greater or equal than 0, because I get then this, and then I have this is greater or equal than 0. Oh, now it's correct. Okay, so for all h greater than 0. Okay, so this is my observation. So u should be positive, and on the other hand, whenever so on the other hand, if, okay, let's say, if A is the region where psi okay, so let me see, because I have by hand, I know what is the solution, so I can plug in, but just, I'm thinking how to do it fast. Okay, let's say, if A is the region where psi is less than 0, less or equal than 0. Okay, then I clearly, the fact that I minimize, but in this case, you can verify that you should be 0. I'm thinking some fast way. I think we have just to verify explicitly that the solution is this one. So set u equal to the max 0 and then u, and we have to verify this guy. Sorry, 0 psi. So now let's compute this guy here. So this is the integral of the max 0 psi, and then we have v minus the max 0 psi. And now this guy is equal to the integral where psi is greater than 0, because otherwise this is 0, of v minus psi, which is greater than 0 because v belongs to k, so v is greater or equal than psi. I think this is the best way. I mean, just something explicitly, because otherwise I have to compute it and it becomes more complicated. There is time for a fast question if you want.
It is in sample 3 and 3b. I think the first one can be done by using density argument and dominated convergence. 3a can be done by using density and dominated convergence, but I don't know how to do the second one, b, cb.
Okay, the first one is the continuity in well, no, you cannot use the dominated convergence. That I'm not sure. You have to use the continuity of translation.
And density argument, right? Yeah, I think you can prove it for step functions first, and then. Okay,
in that case is the same as the continuity, because you approve for approximation, and then you show that is uniformly. Yes. So it's okay. So about the second, does not converge to 0, so you have to show that there are functions with L2 norm equal to 1, which whose distance for the translation is large, so is uniform. Okay, and this you are in what? In R. So let's write the thing. So now we want to show just this part. The norm of the translation. So, and then we have to show that the supremum of when the norm is equal to 1 of u translated 1 over k minus u is equal to 1. Okay? No? Because then it means because the question was that no tk does not converge to identity in norm, and in norm it would mean that tk minus the identity u, the supremum norm of u equal to 1, okay, is non-zero. So this is greater than 0. I just put 1 is uniformly greater than 0. Greater than c, greater than 0. Okay? Let's say greater than c, greater than 0. I just put 1 because at the end you get some constant, which is. So this is the correct quantity. The convergence in norm is translated to this convergence because of the definition of tk. So you have just to find a function in L2 whose translation is translation by k fixed is a constant. Okay, so just define with size 1 over k and height 1. And then you need to have how many k of this guy. So the translation is clearly so we have that the difference in norm is equal to what? Is 1, so it's 2. So for any k, there exists a nu such that the difference is large. So it cannot converge uniformly, but it converges just pointwise. Okay? So I think this is the end. Write me for all the exercises you need to review, because the samples, as you see, are not that difficult. There will be more exercises in the exam. You have only to solve 5. So you can choose which ones you prefer in order to be sure that you get that is not, all the theory is covered. And
Is the level of difficulty same like the sample exam?
Pardon?
Is the level of difficulty same like the sample exam?
Is the level of difficulty?
Similar to the one in sample.
Yeah, but yeah, the only thing I will check in order not to get, as in the first exercise, that the computation was more difficult than the one that I thought. But yes, more or less, yes, this is the level.
Okay.
Okay. So I cannot say it was nice to meet you, but okay. See you the 8th of March.
Thank you, Professor.
Thank you.